All right, THS Chem team, here's your next reaction in line for the chemical reactions that we've been learning. This is called a double replacement or a double displacement reaction. Typically what we have here is an example in the picture shown in front here where you mix two aqueous solutions and you end up producing a precipitate or solid substance that does not dissolve in water. So this is probably the most complicated one. You're going to need your reference table out in front of you, and let's go ahead and take a look at what we need to know about double replacement reactions. All right, first thing we're going to have to review is phase notation. So phase notation is when we are talking solid, liquid, gas, and aqueous. So when we talk solid, liquid, and gas, we're talking about one substance, not a mixture of substances. Aqueous is when we have a mixture of something that is dissolved in water. So if we wanted to actually write out the formula for water with the phase notation, we know that water is H2O. But if we wanted to include the phase notation, water under standard conditions is going to be considered a liquid. So we're always going to put it subscript like our subscripts and put it in parentheses. So it would be a lowercase l for liquid. Salt or table salt is NaCl. And under normal conditions, that is a solid. So we would put a lowercase s in parentheses. Now things get tricky when we start to think about it in water. So salt we know dissolves or is soluble in water. So since it's soluble in water, when we have salt water, we don't write out the water part of our formula. Instead, we are just going to put it as NaCl to tell us that it's salt. And that's when we're going to use our AQ for being aqueous. So when you see this AQ, that's the only one of our phase notations that tells us that we have a mixture in that one formula. So NaCl solid, not mixed, it is just a solid compound. AQ means it is dissolved in water, it is a mixture. Now sand in water, we know sand does not dissolve in water, so therefore it's insoluble. If we were going to write out that formula, we would actually have to do each piece. So sand's primary component is silicon dioxide, and we know that is going to be a solid. And since it's not actually dissolved together, we're going to write out both of them separately. So it has water as a liquid. So this one is an insoluble solid. So it's going to get the solid phase notation, whereas salt is a soluble substance in water, so it gets the aqueous notation when we put it in water. All right, let's move on to the next step. These double replacement reactions are sometimes the easiest to identify because they are the longest reactions we're going to see. They're going to take two compounds and two ionic compounds, and they're going to trade spots with their ions. So as you can see up here, it's kind of outlined with B and D will switch spots. So you now have A with D and C with B. So the ions are just basically trading partners. Okay, so you have ionic equation, plus two new ionic compounds on the product side. Now, like with single replacement, these don't automatically happen. They only happen if we have the right conditions. So the only time that these double replacement reactions occur is if we can get one of our products to either be water or one of our products is a solid precipitate. So this word we've talked about before, but it's going to come up again. Precipitate is related similar to precipitation, where things fall from the sky to the ground. A precipitate in chemistry is a solid, something that is insoluble, meaning it won't dissolve in water, that sinks to the bottom of a solution. And typically, they also change color when they are produced. That means if we were looking at our reaction up here, something up here needs to be either solid or H2O liquid. So this is where things get a little tricky because we now have to figure out how do we know if something is a precipitate or solid in solution. Well, that's where you need your reference table. So open your reference table up to table F. And this is not the easiest table to follow, but is the one we have to use from our reference tables. And so what it's kind of divided into is that you have two sides. You have ions that are considered soluble. So these ions, if they are considered soluble, means when we write them out, they would get an AQ notation. If they are an exception, they would get a solid or S notation. And then the table on the right has that flipped. Those are insoluble, so that means the ones that are insoluble, these ions that are insoluble would get the S notation. The exceptions on the right-hand side would get the AQ or aqueous notation. Okay, so now this is not the easiest thing to follow, so let's actually look at an example and show how to use this table. All right, so here's an example of a double replacement reaction, and we can tell it's double replacement because number one, it's a very large reaction. Number two, the only thing we see in here are compounds. So every single one of these substances in our reaction here in our equation are compounds, and they're all ionic compounds, meaning they have a metal with a nonmetal or polyatomic ion. Okay, so the trick is, think about what's the name of each one of these. So if I look at my first substance here, the name of that is lead nitrate. And you usually are going to focus on the anion or the second ion. So NO3 we know is nitrate. So what you're going to do is go back to your table F and you're going to look up nitrates. And we find that nitrates are right here. They are under the soluble compounds and there are no exceptions. So that tells me that whenever I have a nitrate, it is going to get an aqueous notation. Okay, let's move on to the next one here. Ki. If we were to name this, remember these are all ionic compounds, so you don't have to worry about your prefixes, you just have to name your ions. This is potassium iodide. So we're going to look up iodide in the table. Let's go back to table F. And we're going to look for iodide. And this, let's start over here on the left. Group 1, ammonium nitrate acetate, hydrogen carbonate chlorate, halides. Halides is another way of saying halogens. And you can see that iodine is right there with the halogens. So it is soluble. This one does have some exceptions, except when combined with silver, lead, or mercury. And in this case, we were combined with potassium, so it is not an exception. So in our equation, this one also gets an AQ. So we're mixing two aqueous solutions. And in order for this reaction to take place, one of these over here, either the PbI2 or the KNO3, has to be insoluble. So let's follow the same process here. Again, this is PbI2, so we're going to focus on the anion. This is a lead iodide, so lead 2 iodide. So let's go back to our table, and iodide is still circled down here, is the last one we just looked at. Our exceptions in this case, when combined with silver Pb plus 2, which it is combined with lead in this case, that means it's an exception to being soluble, so it's actually insoluble. So we're going to give it a notation of an S for solid. So PbI2 will not dissolve in water. So from this reaction, this is our precipitate. This tells me that this reaction will take place. All right, and let's just double check our last one here, KNO3. That's potassium nitrate. So we go back and remember what we said about nitrates. Whenever you have nitrate, it will always be aqueous. So whenever you see an NO3 on the end of a compound, automatically tells you that that is an aqueous substance. It can dissolve in water. So because we have this one precipitate, this one product here that is insoluble, That tells us that this reaction will take place. So if I were to actually combine the two liquids or the two aqueous solutions on my reactant side, I would end up with a new cloudy substance in my product side that would sink to the bottom. All right, so that's as far as we're going to go with this round. We are going to do a bunch of these examples in class. So bring your questions to class. And your reference table. We will go through how to use table F and how to figure out the products for these double replacement reactions. See you in class.